Alright, we are up and recording. Alright, well, last class of the quarter for CSE215. So we made it. I have blazing sunlight behind me, but I have curtains.
Well, no, I think the statement we made it might depend on the outcome of the test.
Well, we made it anyway. I have complete confidence in people's understanding of discrete structures. So all you gotta do is prove me right. Alright, well, let's see. So homework 10, only one person turned in their attempt on it. But I want to go through homework 10 anyway because this talks about state machines and Turing machines, which are potential topics on the exam. So I want to run through at least a few of these questions. And for the final, I'm not going to ask you to design state machines or design Turing machines. I may ask you to do analysis on them, but the design is a good way to dig into the analysis part.
As far as analysis, you mean like look at a set of instructions and tell us kind of what it's going to do, or tell you like where it's going to end up?
Exactly, yeah. So the analysis part is here's a machine, tell me what it does. The synthesis part is I want a machine which does this. Show me what that machine should look like.
Okay.
So, and synthesis is usually trickier, but it also requires you to be able to do analysis. So, so let's look at this. So, the first few questions were designing a state machine to recognize certain strings. So if we want to recognize the string 1001, and we assume those are the only inputs, have some starting state. And we want to recognize 1001. So certainly if we get an input of 1, we should go to a state. And this state means, hey, we saw the first character of our input. And from here, we want to see a 0. And if we see that, we go to another state which says, hey, I've seen a 1 and a 0. We're halfway there. And if we're in that state and we see another 0, we go to a state which means I've seen 1, 0, 0. And then from here, if we see a 1, we'll go into a recognized state which says, hey, I've seen a 1, 0, 0, 1. And depending on how we want this machine to behave, we can make these other transitions do a few different things. If we want a machine which you get one shot, if it sees 1001, it goes to a recognized state. If it sees anything else, it says not recognized. We could send all of these other transitions to a state which says, nope, I didn't see a 1001.
Can I ask a question?
Mm-hmm.
The thing I found the most confusing is I could always get from start to finish with the desired recognized string.
Okay.
Do you always have to go from recognized to start again with like a 1 or a 0? Because it seemed like if you had to do that, it'd mess up the strings, maybe?
And this isn't really defined in this question, right? So there's a variety of things we could do. We could have a machine like a combination lock, right? So you type in 1001 and the lock opens, and the machine is done doing anything until you reset it, right? In which case, we wouldn't really care what happens once you're in this state. Or it could be, every time you type 1001, something happens, and then potentially you want to type that again. And so after this state, the next time the person types a 1, we might, first time they hit any key, we might go back to the start state. Or the next time they type a 1, we might actually go to this state saying, hey, I've seen a 1. That could be the start of a new 1001. And a 0 could bring us back here. And it depends on the requirements of the problem. So this would probably be the easiest way to design this. And if we didn't want to do too much work, you know, we could have our 0 and our 1 and our 1 and our 1 and our 0. We could have all of these go to some state which says, hey, you did not enter the correct thing. And then a 0 and a 1 would just leave us in that state. And this is sort of the one-shot version of a state machine. You get to type in 4 buttons, and if they're 1, 0, 0, 1, you end up here. Anything else, you end up in this state that you can never leave until the system is reset. But a more practical version might say, you know, if you type a 1, let's go over here. If you type a 0, that's not a valid start. If you're here and you type another 1, we could stay in this state. If you type a 0, it goes over here, and then a 1 could bring you back here, and from here, a 0 could bring you back. And so what happens now, let's say I type a bunch of 0s, I just keep hanging out in this start state. And now I type a 1 and I go to this state, and maybe I type a bunch of 1s and I stay in this state. And now if I type a 0, 0, 1, I'll go to my recognized state. Well, what is it recognizing? It's recognizing this, 1, 0, 0, 1. And if I type a 0, 0, and a 1, and a 0, and a 0, but over here I type a 0, that brings me all the way back here. And now I could type a 1 and a 0, and maybe here I type a 1. Well, that 1 brings me back here. Actually, it should probably bring me there. And then a 1, 0, 0, 1. I'd be in my recognized state. That's what it recognized.
That's the only part I found super confusing. It's much more clear now. Like, I kept thinking, as soon as you get to recognize state, like, if you want to have it recognize something else, you have to send it back to start with something.
Right, right. And we could do the same thing in the recognized state if this was, you know, a temporary unlock code on the door of an apartment building, right? You type a 1001, it unlocks. You'd like it to reset, which means that, you know, at this point, if the person types a 0, I'm going to go back to the start state. If they type a 1, I'm going to go back to this state which says, hey, I've seen a 1. So now you type 1001, it's recognized. If you immediately type 1001 again, you'll be back in the recognized state.
Is it possible to have a 1 or a 0 take you to the same state? Because that's kind of how I was solving my problems.
You can.
I know that you couldn't go from recognized to start without something, but...
So for example, if we wanted this system to stay unlocked forever, to stay in a recognized state, in other words, recognize any string that begins with 1001, we could do this. We could say, you know, at this point, if you type in a 0, or if you type in a 1, let's just stay in this state. The trick is that, you know, I could type a million zeros and I'll still be in this state. So if we do something like this, here's our start string. If we have a 1, we come over to here. If we have zeros, we stay here. If we have 1, we go to a recognized state, right? This would recognize a 1 followed by any number of zeros followed by a 1. So if you want to do an arbitrary number of something, you can just sort of spin in one state. And when thinking about state machines, I find it useful for myself to try to sort of have a mental description of what each state is. This is the initial state. This state means I have seen a single 1. Or I've seen a single 1 followed by any number of zeros. And this state means I've seen a 1 followed by any number of zeros followed by another 1. And this is potential flashbacks to Engineering 250, depending on how you did state machines in there. Alright, so with that idea, suppose we want to recognize strings of this form. 1, 0 to the n bigger than or equal to 0. So successions of 1 and 0. Oh, someone said in chat, car door locks have an efficient brute force method that keeps a running log of the last 5 digits. So that's another option, is at any point during your input, if you see the correct sequence, you should go to your recognized state. And that's what these lines were doing, basically. If you're expecting a 0 but you type a 1, well, that could be the first one that we were looking for. So we would go back to this state, which means I've seen a 1. And if we're expecting, you know, something else, we can go to another state accordingly. All right, so 1, 0 to the n. So this should pick up, you know, 1, 0, 10, 10, 10, 10, 10, but also the empty string. If n is 0, this should recognize the empty string. So our start state is also a recognized state. And if we're in a recognized state, it means we've seen, you know, if we're in the start state, we've seen nothing. That's a recognized string. If we see a 1 followed by a 0, well, that's a recognized state. If we're in our start state and we see a 0, we don't recognize it. If we see a 1 followed by another 1, I'm going to put that back here. Actually, if we see a 1 followed by another 1, that's not a recognized state, so we're going to go back to the start. Actually, that's not right either. So if we see a 1 and then we see another 1, that's going to go to a state that says we've got nothing. We've got a 1, we'd like to see a 0. So if we see another 1, we'll stay here. If we see a 0, now we've seen a 1 followed by a 0. And this one actually, so again, it depends what we want to do if we get an unrecognized string. So let's just make something that just explicitly looks for a number of 1s followed by 0s. So start state. If we get a 0, we don't recognize that. If we get a 1, we go to a state which says, hey, I've seen a 1. If we get a 0, we can go right back here. And we're back in the start state, that's okay. We're in a recognized state. So we see a 1 followed by a 0, we recognize that. We see another 1 followed by a 0, we recognize that. If we see a 1 and that's followed by another 1, then we don't recognize that pattern. And so we come to this unrecognized state. And if we're at the beginning of this, or we've just seen a number of 1 zeros, and we see another 0, then we go to this unrecognized state. And from here we can just stay unrecognized. And after you do a few of these, you start to develop kind of an intuition for how to piece these together. So question 3 is the same as 2, except we want to start with a pair of 1s. And so how do we do that? Well, we would have our start state, and we'd need a 1 followed by a 1, which would bring us down here. So if we have a 1 followed by another 1, now we're in this state that's recognized, and if we get any number of 1s followed by 0s, we'll still be in this recognized state. And so you can start piecing these things together.
I can't see what you're writing those anyway.
Thank you. There we go. So yeah, make a start state that recognizes a 1 followed by another 1, and have that bring you to what was our start state. Because once we're in this state, we're going to recognize basically 1, 0 to the n. And what I've added here was something which just recognizes a 1 followed by a 1. So if I make that my start and go there, that's going to recognize 1 0 followed by any number of 1 zeros. It is a smiling cartoon person. And then number 4 is 0, 1 to the n, 0. So how do we recognize 1 to the n? Here's a recognized state, or here's a state. If we have a 1, we'll just stay in this state. This is our basic, spin state that stays here as long as we see 1s coming in. So if I have a start state and I wait for a 0, that takes me here. This recognizes any number of 1s, and if I get a 0, that takes me to a recognized state. This picks up 0, 1 to the n, and 0. Alright, so question 5 is a good conceptual question. Can you design a finite state machine that recognizes any string that contains the same number of 0s and 1s? So what do you think about this? Is this possible?
You could have a start state that goes to 1, and then it goes to 0, and then it goes to the recognized state. And if you want to recognize n number of those, you could just go back to the start state, and it's always going to have the same number of 1s and 0s, right?
Possibly. So that's a good analysis, except for if we had 1,000,000 1s followed by 1,000,000 zeros, we want to recognize that as being a recognized string. And so if our 1s and 0s are going to alternate, we can do something like what you just described. But if we're allowing for the case where maybe we get a bunch of 1s first and then a bunch of 0s, we're going to need something more. We're going to need more states, basically. And if we know we have at most 1,000,000 inputs, we could do this with a machine with, maybe 2,000,000 states. Probably more. But with no limit on the number of 1s and 0s that are coming in, to be able to recognize any string that has the same number of 1s and 0s, we cannot do that with a finite state machine. We could do it with an infinite state machine, but not one with only finite states, because we need a state that means I've seen 1,000,000 1s, and that has to be a different state from the one that says, I've seen 1,000,001 1s. Because to get to a recognized state from here is a different requirement. We have to see 1,000,001 zeros, or maybe 1,000,002 zeros with an extra 1 somewhere in the middle. And so that finiteness comes in some seemingly pretty basic behaviors, like just telling if we got the same number of 1s and 0s, we would need infinite states for that.
So this would be like an incredibly task-intensive problem. So it would be like state 1 for 1 1, state 2 for 2 1, state 3 for 3 1s. Because there's no other way to count them that way.
Yeah, and it's even worse than that, because we need a state which doesn't just say we've seen 3 1s, but says, for example, we've seen 3 1s and 7 zeros. And so we would probably have a state that tells us how many more 1s we've seen than zeros. In other words, the difference between those counts. And we would have a state, that we start off where we've got the same number of zeros and 1s. If we have a 1, we go to this, plus 1 state. If we get another 1, we'd go to plus 2. If we get another 1, we'd go to plus 3. If we get a 0, we'd go to like -1. And if we get another 0, we go to -2, and another 0, we go to -3. But if we're in plus 1 and we see a 0, then we're back to recognized. If we're in plus 2 and we see a 0, now we're plus 1 on the number of 1s. If we're -1 and we see a 1, it's recognized. If we're -2 and we see a 1, it's -1, and so on. And so you could do this with, if there's only 2 million bits, a million bits, you could do it with about 2 million states. But yeah, it's a big, horrifying program. On the other hand, this is pretty easy in C, right? Have a pair of counters for zeros and ones and tally them up each time you see a bit, and if they're equal, say recognized. But is there a limit to how many ones and zeros we can do this to in a C program?
Yeah, you can't go above 64 bits.
Yeah.
At the most, right?
Or maybe more if we do our own arithmetic. But eventually there's a limit to how much memory we can store in the machine. If we have 16 gig of main memory, we cannot store a number bigger than 16 times 8 times a billion bits. And so 2 raised to that power, that's the most number of ones or zeros we could possibly count. It's a huge limit, but it's still a limit. So infinity is a big beast. Alright, let's do one of the Turing machine problems, because most of these were synthesis, but this one was an analysis question, question 6. So let's just do that. And we'll wrap it up with that. I'm on Canvas, so I can't zoom very far. Alright, so let me copy this down. This machine, and then we'll see what it does. So what will this machine do to an arbitrary bit string? So assuming we start in S0, if there's a 0 on the tape, it's going to change it to a 1 and move to the right. So if there's a 0, it'll change it to a 1. If there's a 1, it will change it to a 1, leave it as a 1, and move to the right. There's a 1, it'll stay as a 1, move to the right. There's a 0, it'll change it to a 1, move to the right. There's a 1, it will leave it as a 1, move to the right. There's a 0, it'll write it as a 1, move to the right. There's a blank, it will leave it as a blank, and it will move to state 1 and go to the left. And state 1, there's a 1, it will leave it as a 1, go to state 2, and move to the right. So what is this doing? It's taking an n-bit string and turning it into a string of n ones. Why? I don't know. That's what I came up with. And it leaves the blank where it is.
On the test, if you do one of these, are you going to basically just be asking what is the output of it? Or
Yeah,
do we
yeah.
have to redraw? Okay.
Mm-hmm.
Okay.
I can live with 16 times 8 times 10 to the 9th for now. Yeah, me too. This week at least. All right, so these other Turing machine questions I'm not going to go through because I want to get to some review for the final. But you can think about these, try to design these machines, and then check your design by doing the analysis of the machine you came up with. And if you want, you can also use an online emulator and type in your program and see what it actually does to your string, and that would be an interesting test. So append a single 1 to the rightmost end of the string, or replace the first 2 consecutive 1s with 0s. And this is a good one that gets you into the idea of of different states, right? First state, we're looking for a 1. Next state, we found a 1, we're looking for a second consecutive 1. Third state would be, hey, we found 2 consecutive 1s, let's go back and replace them with 0s, and that would have a few states to it, and then you could exit the machine at that point. Have the machine halt. Alright, so you want to talk about the final? So logistics, first of all, so your final exam is Monday, and it's 12 o'clock to 1:50. Our class starts at 12:30, but the exam starts at 12, so don't lose that extra half hour. 12 o'clock to 1:50. It will be in the regular Zoom room. And technically, you do not need to be in Zoom to take the final. The final will open up on Canvas at 12 o'clock under the final exam section on the Canvas page. It's a file that you look at to see the questions, you type up your answers, upload it as a PDF. But I recommend coming into Zoom just like on the midterms, so that if I have to, announce corrections or clarifications, I can do that and you'll be able to hear those. So Monday 12 o'clock till 1:50. Try very hard not to miss the exam, not to come to the exam late. Makeup opportunities are very iffy at this point. So make sure you're here for the exam. The exam will be open book, open note. Okay, we've got a textbook for the course, you've got your notes that you've been taking, you're allowed to use any of those. That's it. Alright, so no online references, no Google, no friends, things like that. And there'll be an honor statement in the beginning, as usual. Include your honor statement in your exam. Don't do it as a separate upload. Don't do it as a submission comment. It's got to be the first thing of your exam. I'll spell that out in the instructions on the exam. But make sure you don't forget the honor statement. And I don't know how many questions, I haven't written it yet, but let's talk about possible topics. And this is really just kind of a synopsis of what we've been doing. And if you have questions about the course that you want to talk about first, or questions as we go through this, just go ahead and say so. Will the Canvas modules be removed locked after today? No, they should not. If they end up locking for some reason, let me know. But Canvas should stay open for some time after the course. So we started with sets. You should know, the definition of a set, including the fact that elements of set only appear once. So if you take the union of two sets, don't list an element twice. Sets are unordered. Curly brackets list the elements inside the set, separated by commas. We have some special sets, including the sets of integers, rational numbers or fractions, real numbers or plain old numbers, The empty set, which is a set containing no elements. Singleton sets, which contain a single element, and so on and so forth. Things we can do to sets include taking unions, operations, complements, subtraction, right? Make sure you understand the idea of A minus B, or A take away B. This is all the stuff in here with this stuff removed. So you're pulling these elements out of that set, if they exist. And this general notion of B bar, that's all the stuff in the universe that's not in B. So this is really the universal set with B removed. The exam will be just like the midterm and just like the homework. So you'll be saving your answers as a PDF file and uploading that PDF online. So it will be like homeworks and midterm. These mean exactly the same thing. It's just two different notations. Alright, so ways to combine sets, unions, intersections, complements, knowing what the universe is, and so on. Subsets, so a subset of a set is just, some collection of elements from that set. including possibly all the elements, including possibly none of the elements. So just grab some elements, 0 or more, and throw it in another set. That's a subset. Power set is a set itself containing all the subsets of a set. Cartesian products is this business of you get a set comprised of these tuples, where this first element of the tuple comes from A, and the second element of the tuple comes from B. And you basically find all the possible ways that you can form a tuple where the first element comes from A, second element comes from B. And the collection of all those tuples is itself a set. And that set's called the Cartesian product. And set identities are these things that look a lot like Engineering 250, where A union B is the same as B union A. A union A is the same thing as A. A union, the complement of A, is the universal set. A intersect the complement of A is the empty set. And all that kind of stuff, up to and including our favorite, right, which is De Morgan's theorem. And there's one form of De Morgan's. The complement of A union B is the intersection of the complements of A and B. So there's a page in the book that covers all of these things, these set identities. All right, functions, we talked about types of functions: injective, surjective, bijective. Do a quick review on those, right? Injective basically means different things mapped to different things. So if I have 2 points over here, if this function is injective, they have to map to different points over here. If they map to the same point, it's no longer an injective function. Surjective just means everything gets mapped to. So if I have, a set of points over here in this set, every one of these has to have an arrow. Some of these points might have multiple arrows. That's okay. As long as every point has an arrow pointing to it, that function is surjective. If there's a point that doesn't have an arrow pointing to it, it's not surjective anymore. And then bijective just means both injective and surjective, which means basically every point here maps to one point here, and every point here comes from exactly one point there. And that's a one-to-one correspondence. Point here, point there. You can find this correspondence between them, and it's unique and well-defined. Domain is the space that you're coming from. Range is the space that you're going into. And to be well defined, we basically need to know that, f of something has a unique value. We can't say, this point goes to 5 different values. That's not a function. So, and it's the same in mathematics. If we have a function f of x equals, there's always, exactly one thing that we can fill in the blank with. We can't say, the sign of x is, well, it could be 2, but it could be -6 also. That's not a function. It's not well defined. So vertical line test in math. Summations are, these sigmas. And there's an index, and there's a lower bounds and an upper bounds on the index, and basically you evaluate this when I equals this value plus 1, this value plus 2, all the way up to this value, and then you just add all of those together. And that's the value of the summation. If you see something with a double summation, right, easiest way to deal with it is first do this summation, replace this with just a plain old expression without the sigma, and now you have, a simple summation question with some big long formula in here. We talked really briefly about matrices. I'm not likely to ask you a lot about that, but matrices, 2 by 2 arrays of numbers, and the main thing to know is that we can add and subtract matrices, we can multiply them, but the multiplication is weird, and there's no rigid way to do division of matrices. We can define an inverse sometimes, but sometimes inverses don't even exist. So matrix math is not like regular, math on real numbers, including the fact that it's usually not commutative. A times B is not always the same as B times A. But you'll spend, when you do CSE2 or Math 215, or if you've already done it, that's all about matrices. So you'll get that there. All right, chapter 3. So big part of the course was about propositional logic. So know what a proposition is. Declarative statement that has a truth value. And we have ways to combine propositions to make new propositions. Conjunction, which is an and. Disjunction, which is an or. Inference, which says, if P, then Q. Are we likely to have multiple proofs on the final, like on the midterm? You might see 2 proofs. It's not going to be, a lot of proofs because we've got the whole quarter worth of material to go through. And I don't know how many questions there are. But if I gave you 10 or 15 questions, I think 2 proofs would probably be the most. But you can expect a proof that involves mathematical induction, because that's a big part of the course, and maybe a proof question that just uses, some of the rules of inference, those things from, like, I think it was section 3.5, those kinds of questions. But we got enough other material to test on. All right, so logical equivalence, knowing if 2 statements are logically the same, and sometimes, we have rules that tell us, for example, P and Q is logically equivalent to Q and P. And, not P and Q is logically equivalent to not P or not Q. There's De Morgan's theorem again, right? And on this note, right, my suggestion is don't try to type your final exam unless you've got a really rock-solid typesetting system. But a lot of times people who type up their exam, they end up using, like, different symbols. Like they'll use a dash instead of this little hook symbol for not. And sometimes I can figure out what you're trying to say, but I have to kind of like do some interpretation for you, and I'm not gonna want to do that on the final exam. So unless you can, absolutely type things that look the way we expect them to look, write it out by hand. Write neatly, right? But get some paper and a soft pencil and a good eraser, and have a way to scan that, right? Take a picture of it and upload it, and write out your answers. And it's going to be faster and less error prone in most cases. All right, so rules of inference, logical equivalence is a quantifier. So quantifiers are these backwards, upside down things. So the universal quantifier, the existential quantifier. For all x, something is true. There exists an x such that something is true. And we usually have, a universe specified. So for all x in z, or there exists an x contained in z, or something like that. And then fallacies, there's 2 fallacies. So fallacy of affirming the conclusion or denying the hypothesis. And these are kind of the counterposes to direct reasoning or detachment and indirect reasoning. And so it's the backwards, incorrect way of trying to do those laws of logic. Slip days are not the same as extended time on an exam. The slip days you haven't used, you don't get to use those for anything. So they don't get you extra time. If you have an extended time allowance for the final, though, through the DSS office, just take the extended time. And Canvas will, say that your submission is late and it'll be in red letters or something. Don't worry about that. Okay, if you have a DSS allowance, then you and I have already talked about this. And if you don't have to turn your exam in until some later time, right, that's the time that I'll use to decide if your submission is late or not. So just take the extra time you need. Don't worry about what Canvas says. If you have extended time and your exams are back to back, send me an email today, right after class, and let's talk about it, because you'll probably just want to start the second exam late. And that's fine. We just need to pin down exactly what time that's going to be. So yeah, send me an email. All right, so proofs. Basically, two approaches to proving things, directly and indirectly. Direct proofs start with what you know and work until you get to what you're trying to show. Indirect proof start by assuming what you're trying to show is false, and then use what you know and argue to a contradiction. Argue to basically, false equals true. And then you can go back and say, therefore, this original assumption that this conclusion was false must be wrong, so the conclusion must be true. So that first approach is a direct proof. The second is called an indirect proof, or sometimes a proof by contradiction. All right, good sample proofs that we've done. Proofs about even and odd numbers. I'll give you a heads up here. If I ask you to use propositional logic to prove something about even numbers, and you do a proof that uses, facts about doing things modulo 2, you don't get credit for that, right? We have a lot of different ways of doing things at this point. We could prove, that the sum of two even numbers is even by using propositional logic. We could do it by working modulo 2. We could do it probably by using some other aspects of number theory, right? But I'll be very clear about how I want you to prove these things. And if I want a proof that uses propositional logic, right, and you shortcut it, then you won't get credit for that. So plan on, maybe a proof related to even and odd numbers along the lines of what we've done in homework and done in class and so on. Basically, you're working from what you know to show something that you don't yet know, right? But every step of a proof has to follow from what you've done so far and or from various laws of logic, propositional logic. So yeah, when we're doing these proofs on even and odds, the only thing we really know is that an even number can be written as twice an integer, an odd number can be written as twice an integer plus 1. And that's what you have to build from. When it's all right to start with what you don't know, that's a proof by contradiction. Or, some kind of contingent proof. Prove that if P is true, then such and such happens. Well, we can assume P is true. That's what we're trying to show, is that if P is true, then something else happens. So you can start by assuming P is true. That doesn't prove P is true, right? It just says if P is true, then other stuff. All right, number theory, we talked a lot about divisibility. Remember this divisibility divides symbol, right? 3 divides 15. So 3 vertical bar 15 means 3 divides 15. 15 is divisible by 3. There exists an integer such that 15 equals 3 times that integer, and so on. Okay, don't let your pen get sloppy and start thinking about this as being 3 divided by 15. All right, this is a proposition. This is the proposition that 3 is a factor of 15. So if you're doing a proof and you're writing, propositions, every statement of a proof has to be a proposition. This is a valid proposition. All right, congruence. So congruence, remember when we say, something like 17 is congruent to 2 modulo 5, what we're saying is that this and this have the same remainder when you divide by 5. We're also saying the difference of these two numbers is divisible by 5. So 5 divides 17 minus 2. But for working purposes, we usually think of it as the same remainder comes out of dividing this or this by 5. But remember this business of remainder, there's a caveat there, right? Technically 17 divided by 5, you know, we normally think of that 3 with 2 left over, but it's also 2 with 7 left over. It's also 4 with negative 3 left over. When we talk about remainders like this, we're thinking about this, right? A remainder between 0 and this thing minus 1. And the fact that there's always, you know, a unique remainder that's in that range, that's what we call the division algorithm. So the division algorithm is basically this fact that when you take a number, a, and you divide it by m, we can find a remainder between 0 and m minus 1. Alright, in prime numbers, you should know the definition of a prime. You should know that 1 is not considered prime. Fundamental theorem of arithmetic is that every positive number can be written as a product of primes in a unique way, where unique means, you know, other than rearranging the order in which you multiply these things. There's an infinite number of primes, but the number of primes up to n approaches log of n when n gets really, really big. That's the prime number theorem. Greatest common divisor is the largest positive integer that divides two other integers, and there's a way for finding the GCD, which we call the Euclidean algorithm, so you should know that algorithm. Modular exponentiation, the way we're teaching it in this course, is this very particular approach to writing, you know, something like, you know, 7 to the 123rd. And this approach goes as follows. If we want 7 to the 123rd, we can write 123 as 64 plus 32 plus 16 plus 8 plus 2 plus 1. And so if we find 7 to the first, 7 squared, 7 fourth, 7th, 8th, and so on, we find each of these by squaring the term before it. And then in this case, we would take 7 to the 1, 2, 8, 16, 32, and 64 and multiply those. And that will give us 7 to the 123rd. But we do this without having to actually multiply 7 by itself 123 times. But modular exponentiation, right, the idea is we find 7 raised to successive powers of 2. Why is that important? Because we can write a computer algorithm to do this. If you just look at a number and you say, well, you know, I know what this is and I know what that is, and if I multiply them, I'll get that. Well, that works great for you, but how do you teach a computer to do that? So this is an algorithm that you can teach a computer. It's very programmatic, right? So that's what we mean by modular exponentiation. Fermat's little theorem is this idea of if you have numbers that are relatively prime, we get this property that a to the p minus 1 is congruent to 1 mod p. And so we can use this to leapfrog our way up to a large power of something modulo a prime, or something relatively prime to a. We can leapfrog all the way up, because if a to the p minus 1 is congruent to 1, we can raise this to a gazillionth power, and it's still going to be congruent to 1, because 1 to the gazillionth power is still 1. So we can sort of, you know, make all this progress in moving up to a large power, and then just do what we have to get from that large power up to the power we actually care about. That you can also teach a computer. It's a different algorithm. Alright, let me see. Looking for something. Applications. We talked a little about parity and check digits. We talked a lot about cryptography. Main things I want you to know from cryptography. You know, the basic idea of encryption or a cipher, right? Change something into another form. Caesar cipher is a shift cipher, where you just, you know, add or subtract something from each letter. There's substitution ciphers where you just replace, and we talked about a number of versions of that. Key concept I want you to know, though, is the difference between a symmetric versus an asymmetric. A symmetric cipher, you have one password for encrypting, you have a password for decrypting, but those two passwords are related to each other. And in general, you can infer one from the other. An asymmetric cipher, which is a public key cipher like RSA, the way you encrypt and decrypt are in some sense unique from each other. If you know how to encrypt, you don't necessarily know how to decrypt. So we have, you know, separate encryption and decryption keys, and knowing one doesn't give you the other. And that's the thing that makes, you know, like e-commerce possible. All right, mathematical induction. So definitely know this, definitely be prepared for a question on induction. Remember, 2 steps, basis step and an inductive step. If you're trying to prove something about a family of propositions, state what that family of propositions is. Don't ever write a proof where you start talking about P of 1, P of n plus 1, if you haven't told the reader what P of n is. What is this proposition P that we're talking about? So start off by stating what you want to prove, state a family of propositions, state that you're trying to prove, you know, P of n for all n bigger than 5 or something. Make a basis step, you know, prove P of some particular value, which you do by demonstrating, and then go about the inductive step. The inductive step says, if P of n, then P of n plus 1. So what do you start with? P of n. That's your first statement of an inductive proof. And then probably write out what P of n says, and then start doing your logical reasoning, things you know about numbers and so on and so forth, until you get to something that shows you P of n plus 1 is true. At that point you can say, therefore P of n implies P of n plus 1, therefore by mathematical induction P of n is true for all n bigger than or equal to whatever your base case was. Right, so again, reasoning from what you know or assume to what it is you're trying to show. Alright, recursive functions we talked about a little bit. This is the idea of expressing something in terms of other values of that same something. For example, if I want to write n factorial, I could say, you know, n factorial is just n times n minus 1 factorial, where n is bigger than 1, and it's just 1 if n is equal to 1. So there's a recursive definition of factorials. And there's no dots in here, there's no, you know, product symbols or summation symbols or something. This is just, you know, if I have a value of n, and I want to find what n factorial is, it's just n times n minus 1 factorial. And without this, I never actually get to a value, because, you know, 3 factorial is 3 times 2 factorial, 2 factorial is 2 times 1 factorial, 1 factorial is 1 times 0 factorial, 0 factorial is 0 times minus 1 factorial, and I keep doing that, I'm never going to find a number that I can actually use. So we have this extra, you know, initial condition or base case which says, oh, and by the way, 1 factorial n equals 1 is just 1. And this is tied into recursion and mathematical induction in ways that will become more apparent in winter quarter. All right, how many problems will we have? I do not know. 10 to 20, I would say. Probably closer to 10, but I haven't written the exam yet. I would like to have more smaller problems rather than fewer large problems. So, but we'll see what I come up with. But also, you know, problems usually have multiple parts. So you might have one problem on counting, but, you know, it might involve several questions that require the use of the product rule, the sum rule, and so on. All right, so pigeonhole principle is basically, you know, if you have n objects and fewer than n containers to put them in, you're going to have to double up at least one in one container. And we saw some applications of that to counting problems. And then the other part of counting was product rule, sum rule. Product rule, if we can think of a task as a series of subtasks performed in succession, we can multiply the number of ways to do each subtask. That's the number of ways to do the main task. Sum rule, if you have a choice of doing one of multiple tasks, then the number of ways to accomplish your original task is the sum of the number of ways to do each of those possible subtasks. And we often take combinations of these. So if you have to order a soup and a salad and then either a dessert or a coffee, right, there'd be a combination of product rule and sum rule there. Principle of inclusion, exclusion, think of people, you know, going to the movies. And, you know, 5 people have seen Star Wars and 10 people have seen Star Trek and 3 people have seen both. And so how many people are in this group? And this is all wrapper around this idea that if you want to find the number of things in a union, it's the number of things in each set minus the number of things in the overlap. Because if we just add the size of these and there's something contained in both of these, those elements in the intersection get counted twice. And so if we subtract off one copy of the size of that intersection, we end up with the size of the union. Yeah, basically product rule is just multiplying the number of ways to do each task. Sum is just adding them. So let's do a simple example. So pick one salad out of 3, one drink out of 5, and one entree out of 7. So you can make this a succession. So your goal is how many ways can I order a meal? And ordering a meal means doing all of these things. Well, I can make it into 3 subtasks. Task 1 is to pick a salad. Task 2 is to then pick a drink. And task 3 is to then pick an entree. And the number of ways I can pick a salad is 3. Number of ways to pick a drink is 5. Number of ways to pick an entree is 7. And so that's a total of 105 ways that we can pick our meal. So that's a product rule. A sum rule would be, you know, choose a soup or salad. And there's 5 soups and there's 6 salads. So here I'm going to perform either task 1, which is to pick a soup, or I'm going to do task 2, which is to pick a salad. So we add those together and we get 11. That's the sum rule. All right, and then permutations and combinations. Permutations are ordered, combinations are unordered. And a permutation being an ordered collection of objects, we usually think of as this. This is the number of r permutations of n objects. Number of ordered ways we can pick r things out of n. And this turns out to be n factorial over n minus r factorial. But it's really just the product rule. If you're trying to pick r things, we have r tasks. Pick the first thing, pick the second thing, pick the rth thing. And the number of ways we can pick the first thing is n, the number of ways to pick the second thing is n minus 1, and so on. And if you take the product rule of those, you'll end up with a big, long, messy version of this formula.
And you're okay with us doing the arithmetics on a calculator, but write this down, right?
Yes, so thank you. So you're okay using a calculator to do the arithmetic. What I most want to see is this and this. and then you can go ahead and break that down to a number, and see if that number is reasonable, for example. But if I see this and I see this, I'm pretty happy. If I see a number and I don't see these, I'm fairly unhappy. If I see a number and the number's wrong and I don't see these, it's a 0, because I have no idea how you got that number. So these are super duper critical. And then
Go
ahead.
Can you show me a few examples of the permutation and combination in some examples to give me an idea about which one should I use for the question get asked in an exam?
So pick 5 people from 7. So you're just picking 5 people to send on a errand somewhere, right? It does not really matter what order I pick these people in. I'm just trying to choose 5 people out of 7. That's an unordered combination, so this would be C 7, 5, which we also write sometimes as this. And remember, combinations are the same as permutations, but we also divide by r factorial. This is factoring out the different ways we could arrange these people. So pick 5 people from a group of 7. That's 7 choose 5. It's C 7, 5. Pick first, second, and third place from a group of 10 people. Well, now we're choosing one person to be in first place, choosing a person to be in second, choosing a person to be in third. We're still picking 3 people out of 10, but the order in which we pick them is important, right? Because if I pick, A, B, and C to be first, second, and third, that's a different selection from if I pick, B, C, and A to be first, second, and third. So this would be a permutation. And there's no hard and fast way to detect whether it's order or unordered. You kind of have to think about the problem. And if you're unsure, you could try asking me during the exam. I may or may not offer an answer or some help. But you can also, let me know on the exam, like, I'm not sure, but I think this is unordered because such and such. And then go ahead and, if it's unordered, do a combination, for example. And again, I'll be in Zoom the whole time, so don't spend your whole time during the exam sending me messages looking for help. But if there's something that's really unclear, that you're really stuck on, you can try sending me a message. I think on the midterm, I spent most of the exam answering questions, and I started falling behind on this and so on. So yeah, but feel free to reach out. All right, and then Pascal's triangle is just that fun triangle that you did for your second programming assignment. And the main thing to know is that, each of these is a combination. And if you just write the combinations, n comma r, that'll be row n element r. Binomial theorem is another thing that we used combinations for. So if you want to know what you get when you raise something to the 4th, well, there's going to be an x to the 4th, an x cubed, an x squared, an x, and an x to the 0. And these exponents always add up to 4, so it's x to the 4th, x cubed y, x squared, x y cubed, and y to the 4th. And the coefficients come out of Pascal's triangle. Alright, so we can multiply this out without having to do too much work and know it's x to the 4th plus 4x cubed y plus 6x squared y squared, etc. That's what the binomial theorem tells us. All right, and then we're down to our last topics for the unit. So graph theory, which was 2 weeks ago. And understand the concept of a graph. It's vertices and edges. The way we draw it is not significant, but the connection among the set of vertices is significant. If these two vertices are connected by an edge, right, that's an immutable fact of the graph. If we draw those two vertices on opposite ends of a page, we would have a very long edge, but the fact that they're connected by an edge, that's what's significant. There's directed graphs where these edges have arrows on them. There's undirected graphs where we just have, just a line, and we'd say there's an edge. Directed, we'd say there's an edge from one vertex to another. There's also weighted graphs where these edges have, numbers associated with them, which could mean different things. Could be distance, could be time, could be cost, could be, who knows. The degree of a vertex is the number of edges touching that vertex. If it's a directed graph, we have in degree and out degree. And the in degree is the number of edges going in to that vertex. The out degree is the number of edges coming out of the vertex. So it's named with respect to the vertex itself. And we had some theorems, right? The total, the sum of all the degrees of all the vertices is twice the number of edges. And for a directed graph, the sum of the in degrees is the same as the sum of the out degrees, which is the same as the number of edges. And you can convince yourself of that because, if we have an edge coming out of a vertex here, that's going to increase the out degree by 1. That has to go to a vertex somewhere, which is going to increase the in degree count by 1 also. And each edge we draw increases both of those by 1. What else have we got? Euler paths. So Euler paths, we travel along each edge exactly once. Hamilton paths, we visit each vertex exactly once. And you did some homework questions on that, and we had some theorems for when we have an Euler path or not. Bye. Representation of graphs. So we saw a few ways to represent graphs, such as in a computer. An adjacency list, where for each vertex we list the vertices that are adjacent to it, meaning connected by an edge. We can make an adjacency matrix where we list, vertices on 2 dimensions, and we put a 1 or some kind of notation if there's an edge from one vertex to another. We can also represent weighted graphs like that. And an incidence matrix where we list for each vertex the edges that are connected to it or incident to it. Isomorphisms of graphs. So this question of when 2 graphs are the same, which means basically we can rearrange their vertices. Bye, have a good time. All right, I'll see you tomorrow. All right, bye. And so if 2 graphs are isomorphic, you can find a one-to-one mapping between the vertices of one and the vertices of another. Dijkstra's algorithm should be on here. It didn't make it on here. But you will almost certainly see a Dijkstra's algorithm question. So make sure you're up on Dijkstra's algorithm. And then grammars and languages. So this is what we were doing the past week. So phrase structure grammars, this idea of, a set of symbols, a set of terminal symbols that make up our final strings, a start symbol, and then a set of production rules. And it's a general model for how we can represent strings that belong to a language. And so it's a way we can do things like parse out, a program that we're going to compile, see if it's a valid program according to our language definition. And so you might need to analyze, you know, a phrase structure, grammar, and show me some strings, or tell me if a string belongs to that that language. And so you start with the start symbol, and you use the production rules to change the start symbol into other strings, and you keep doing this until you get to a string comprised just of terminal symbols, and then that string is part of the language. Finite state machines, we know these from 250, right? They're systems basically described with, you know, a present state, an input, a next state, and an output. And they just roll from one state to another, pulling in input, possibly generating output, and changing to new states based on what state they're in and what they're being fed. State diagrams are ways to represent and analyze these. And then the homework questions, right? So being able to recognize strings with a state machine. So starting with an idea of a start state or an initial state, and taking an input string following transitions, and if you get to a recognized state, then we say that the machine recognizes that string. And there could be multiple recognized states, but it's a way to do, you know, different kind of parsing. And, you know, we mostly play with binary strings, but I mean, you could make a state machine to parse a C program, and every time it gets to, you know, a certain state, it means this is a valid C program. And so if you write a function, you know, after you ingest the last curly bracket, it might move to this recognized state. And then if you start writing another function after that, it would move to some other intermediate states, and when you hit the closing bracket for that, it would move to a recognized state. And if you have a number sign include statement, it would be unrecognized until you got to the end of that, and then it would be back in a recognized state. So you can use this idea more generally. And then Turing machines, right, which are these 5 tuples, and that's, you know, what we started our homework, or we finished our homework discussion with. So, you know, present state, input, next state, output, and which way to move the tape or the read-write head. And you should know that Turing machines are universal. They can do anything that we can do with, you know, a general von Neumann architecture. And that's pretty much it. That's been our last 11 weeks is all of this. So, other questions?
You mentioned that the Pascal triangle can use the commutation answers.
Pascal's triangle is a way to find combinations, right? So if you write this out, each number that we write in this is a combination, and in particular it looks like this. And it's just a good thing to know. Now, if I want to know what 3, 2 is, I'm probably just going to do 3 factorial over 2 factorial times 1 factorial, which will be 6 over 2, which is 3. Right? That's a pretty easy formula to apply. But if I know Pascal's triangle, right, I can see that this thing should be that. So I know 3, 2 is equal to 2, or 3 choose 2. But the main purpose of Pascal's triangle is to be able to make statements or do analysis on these combinations. For example, we know that in Pascal's triangle, each item here in the middle is the sum of the 2 items above it. So just by looking at this, I know, for example, that 3, 2 is going to be 2, 1 plus 2, 2. And maybe that's useful somewhere down the road.
There was that homework problem that was, you know, what combination from, you know, it's like of the set, you know, 1 to 10 or whatever, what combination out of these 7 elements?
Yeah, yeah.
Well, in that case, you go to row 10, pick 7, 8, and 9, and add those.
Mm-hmm.
7, 8, 9, and 10, and add those numbers together.
Right, right. Which may not help us. You know, Pascal's triangle may not help us with that too much. But it's sometimes a useful way to look at things. For example, if I wanted the total number, yeah, it was an awesome train. If I wanted the total number of subsets of a set of 10 things, right, it would be 10 choose 0 plus 10 choose 1 plus all the way up to 10 choose 10. Well, I might remember that, you know, the sum of the elements in each row of Pascal's triangle is just 2 to the n. And so if I actually calculated each of these 11 expressions and added them together, I would get 2 to the 10th. But, you know, this is the number of ways I can choose one thing out of 10, the number of ways I can choose 2 out of 10, the number of ways I can choose 10 out of 10. The sum of these is just the total number of subsets of 10 elements. And you know, I think week 1 we had this idea that the number of elements in the power set of A is just 2 raised to the number of elements in A. So if a set has 10 elements, the number of elements in the power set is 2 to the 10th. Well, that's the number of subsets. And this is the number of subsets with 0 elements, with 1 element, with 10 elements. And since any subset has somewhere between 0 and 10 elements, if I add these up, I should get my total number of subsets. So not a lot of take-home value from that as far as, you know, so what do I need to know about this for the exam? But just know, you know, Pascal's triangle, the elements are combinations, and that each row is the sum of the two things above it, and that's probably plenty. All right, well, send me an attendance ping, and I am happy to let you out 2 minutes early, since it's the last day of class. But thank you, everybody, for the quarter. It's been a fun class for me. Hopefully it's been useful for you. The topics we've covered will undoubtedly come up in the future as you continue studying computer science. And you know, the ones that are really important you'll see again, you'll learn again, and they'll make even more sense the next time. But most of the stuff will be at work at some level in a lot of the stuff that you're doing in computer science. So so hopefully it's been interesting, and hopefully it'll be useful. For the final exam, go over your homework questions, review your notes, but mostly look at homework questions if there was something you weren't sure about, or you know, you had to get a lot of help to get done. Go back and rework some of those questions. If the questions came from the book, look at other questions similar to that. The textbook, each chapter ends with supplemental exercises, and I think the even questions all have answers in the back, so you can pick out sample questions, work out solutions, and then look at the answers and see how you did. And if you can succeed at homework questions, you're probably in really good shape for the final, because it's going to be pretty much just more of the same. So not planning surprises there. All right, cool. So have a fantastic afternoon. Have a great weekend. I will see you possibly at 10 o'clock if you're in the 10 o'clock section of 224, and I will definitely see you at 12 o'clock on Monday for this class's final. So have a good one, and I will see you next time.
I do have a question about something I couldn't understand from the homework. Well, from the class-based homework. It's about Djikstra algorithm, and I'm still kind of struggling about how to properly do it, I guess. I looked it up, but the way other people did it was kind of different from what you did.
You want to hop into office hours for a minute and screen share?
No, I'd like to have you kind of show me, kind of remind me of like how to do it exactly. Because I remember the homework and you gave me feedback saying